Hello, this is Scott Bankafear, and this is the Design Day presentation for the Automated Build Surface Feed System for a Micro-3D printer, with the addition of our pivot to a Build Surface Feed System for a COVID printer. This is the team 19101, and as I said, I am Scott Bankafear, and my team includes Miranda Albo, Sean Donnie, Harsha Donraj, Alex Dumas, and Abdi Tassir. Our sponsor is Eric Orwell, owner and founder of Micro-FDM in Phoenix, Arizona. When Eric came to us in August, we talked about how he was tired of having to change the build platforms for a 3D printer. He realized that in the last 2 decades, 3D printers have become commonly used for about every industry on a daily basis, but lack the ability to make large numbers of parts. So we have created a build surface feed system that allows the printer to complete multiple jobs with limited human interaction. Our goals for this project were to minimize the amount of human interaction with the printer to maximize part production, also to allow for multiple prints to be printed over a certain amount of time, and to be able to mount this feed system to a custom 3D printer in order to print micro parts for Micro-FDM LLC. To be able to accomplish this task, we needed to we showed that this had not been done commercially, and then we started to brainstorm on how we could get this done in a variety of ways. Our first idea for this was a PEZ dispenser, which basically fed down each build surface platform down a track and then fed it into the printer. We realized this wasn't the easiest way, so we went to a tread idea, which you will see later on in the presentation. We also wanted that our system to be reliable and robust, but not to be costly or be complex.
Here's an overview of our major system requirements. Our system utilized interchangeable build surface cartridges, each with an integrated heating element and glass printing surface. Our system was required to hold at least 10 of these cartridges at any time, as well as move them in and out of the 3D printer they are designed for without human intervention. Additionally, our system needed to lock each cartridge into place while prints were ongoing to prevent print failures and ensure dimensional accuracy of the parts produced. Shown here is a rendering of our feed system design. Major components of our system are an aluminum frame, 2 parallel track assemblies, a linear actuator assembly, and a cartridge locking system. Before running, 10 cartridges would be loaded into slots between the track assemblies by an operator. Each track is driven by a stepper motor, which allows the precise positioning of a cartridge in front of the printer build plate. Once an empty cartridge is positioned next to the printer build plate, a linear actuator mounted with a pair of electromagnetic solenoids would connect with the cartridge and push it into the printer, where the locking system would clamp the cartridge into place. The printer would then receive a signal from our system to begin its next print job. Once a print is completed, the printer would signal our feed system, which would then use the same linear actuator to pull the cartridge and completed print back into the original slot between the tracks. Tracks then move down to align a fresh cartridge with the printer plate, and the sequence repeats. Since the tracks have space for 10 cartridges both above and below the printer build plate, this design allows the printer to produce and store up to 10 completed parts without human interaction. Here's a more detailed view of a single track assembly. Each tread runs over a drive sprocket, a guide wheel, and a tensioner assembly. Each tread is made of 52 identical links, and each link is assembled from 2 printed halves. Every effort was made to make our system from 3D printed parts to reduce fabrication costs and allow for quick design iterations if changes needed to be made. The frame itself was fabricated from laser cut aluminum, and the various bearings, shafts, and mounting hardware were purchased, but otherwise the rest of the mechanical parts of the system were made with a 3D printer.
Okay, so here we have the feed system that we designed and built. So unfortunately, we weren't able to get both of the tracks on it, but we were able to test out the track that we actually got mounted on there with the stepper motor, and we will demonstrate that in a near future slide. Okay. Okay, so here we have a picture of the full system, well, at least the electronic aspect of it. To the left is an Arduino Mega with its components, which acts is basically the feed system. And then to the right of the power supply is an Arduino Uno, which is acting as the 3D printer's control board, along with two stepper motors. And we will demonstrate this setup in the next slide. Alright, so here's the video I was talking about earlier. So we attached the Arduino Mega stepper motors to the 3D printer, and then we gave the Arduino Mega 6 control buttons to control each component. Alright, so right now I just pressed the enable button, which enables the Arduino Uno to start moving the Z-axis of the 3D printer. And then to make a move up, we enabled another button onto the Arduino Uno. And then I just pressed the disable button, so that will stop the printer from moving. And then right now there are 4 buttons to the feed system. The one I'm pressing right now extends the actuator, and the one right next to it, it retracts it. Okay. And then there are 2 other buttons that I mentioned, that are to the motors of the feed system. And these are the motors that would go on the tank treads. And that video will be at the end of this one. It's very short. Okay. And then the protocol that's being used to communicate between the 2 Arduinos is I2C. Alright, so here's the video.
Hi, I'm Miranda Albo, and now we're going to pivot onto the COVID-19 response from our sponsor. So first, since we know that's been a big issue affecting our world right now, Eric, our sponsor, came to us with the idea of using our concept and adapting it to a typical 3D printer to automate these face printing shields that you see here. So the objective first is to create a new build surface feed system within a few weeks, and our role is more as consultants and to give advice and any guidance for any hurdles that came up. And so the design concept went back to one of our original ideas where we have less cartridge spots, and it's not a tank tread, but we have 6 slots that can rotate up and down that can be integrated with a standard 3D printer. And now here is a animation of what the build surface feed system for this printer is going to look like. And then here is just a video of it printing and how it's responding to doing 4 layers, and for a print like this with 4 of them at a time takes about an hour to make in total.
Hi, my name is Sean Donnie, and today I'll be talking about the deliverables of our project. First and foremost, our first deliverable was the original build surface feed system, which Micro-FDM took the liberty of taking and completing its finishing parts, as well as have our own members come over and work on the printer. Our next deliverable will be the final report, which will be due in the beginning of May. This final report will include the drawings, SDD, and all other relevant information for the original build surface feed system. Next, we will have the video of the original build surface feed system and the COVID printer build surface feed system that Micro-FDM has been working on. Finally, this final presentation will be the last deliverable for this project.
Hi, I'm Harshad and Raj. I'll be talking about the lessons that we learned in this project. We as a team have learned many lessons throughout this project, and we would like to share some of the insights. Even though we thought we had a perfect project schedule, we still slightly fell behind towards the end, and what we learned in this project is that a project is never set in stone and is always subjected to change. And now as a team, we understand flexibility is the key while doing project scheduling. Initially, our project was to create a Micro-3D printer along with the automated build surface feed system. This was something we set out to do, but due to time constraints, it did not seem possible. And now we have a better understanding of time constraints and what needs to be done well in advance. Integrating the build surface feed system with the printer while not interfering with the operation of the printer was a hurdle that we learned to jump. We really want to thank Eric, our sponsor and the co-founder of Micro-FDM, for helping us. We really appreciate his thoughtfulness to adapt our project to help the healthcare systems amid COVID-19, and for believing in our team and being supportive and acknowledging the idea of a project development. Finally, a big thank you for Professor Gary Redford and the University of Arizona Engineering Department for guiding us through this project for the entire year and for teaching real-life, long-lasting engineering lessons. Thank you.